in a plane. Any sort of discrete walks you have in a plane. And it was done in such a way to be highly algorithmic so a computer can do a lot of the work for us. So, looking in the two-dimensional square lattice, and we have a set of steps, and we're not taking steps to the left. All of our steps are going to the right or up or are vertical. We want to count all possible walks of a certain length, and we could brute force search this, looking for one value, but we can use generating function relations to do something a bit better, and which can end up leading to faster results.
So these are non-intersecting, non-self-intersecting walks, right?
Yes, these are self-intersecting walks. So as I mentioned, the earlier motivation came from physics. Kernel method has received attention lately, but the Guild of Kernel method people, I don't like the method because it's not as intuitive. Our method is a lot easier to understand combinatorial. I found it to be much faster, and it's a lot easier to produce. But the main part is a little bit the same. Trying to picture an entire walk is difficult. Try and break the walk down, as Anthony did, and that's dynamical programming. So I use the term walk to indicate any sequence of points in the xy plane, and the steps are just the differences in the differences. I use bridge to mean a walk, an unbounded walk that begins at the origin, ends on the x-axis. Bounded bridge for one that doesn't go above a certain value or below a certain value. An excursion is a semi-bounded walk. Well, you can read that. A free walk ends anywhere, and a meander is a semi-bounded free walk. Key points from here: the length of a walk is the sum of the x values of the steps, and the size of a walk is s.
Semi-bounded means on one side.
Yes. So here we go. Here's some walks. So assuming these all start at 0, 0. This would be considered an excursion of length 1 or of length 8, and this has size 9, or no, sorry, size 8, because there are 1, 2, 3, 4. The steps are 0, negative 1. 1, 2, 3, 4, 5, 6, 7, 8.
So again, what was the excursion? What makes that an excursion?
Not semi-bounded, and it starts at the origin and ends on the x-axis.
Semi-bounded was.
It's also a bridge.
Non-negative, essentially. It is typically what it's going to be referred to as.
It's also a bridge.
Yes, it's technically also a bridge. Yeah, every excursion is a bridge. And all of these are built from the steps, from this step set. And so that has size 8, this has size 9, this has size 9, this has size 7. That size is the number of steps to go from here to here. Length is the distance you've gone. Well, the horizontal distance. Alrighty. Some other definitions. I'm going to refer to the y value as the altitude of the walk, and the interior of walk consists of all the points other than the endpoints. An irreducible walk, for the most part, is going, well, not for the most part. For most of the cases that I looked at, I considered them to be ones where the interior has strictly higher altitude than the lower endpoint. So, this is not irreducible because this point is back on 0. But this is considered irreducible because we never touch the axis until the end. Some other definitions of irreducible, which will hopefully be apparent from the context. Irreducible is sometimes referred to walks that do not touch the final altitude until the final step. So this is also irreducible in the sense that it doesn't touch this altitude until the final step, ignoring the first part. Okay. So let's start by begin by choosing our dominions to be both bounded above and below. So assume the walk is free. We can end anywhere, as long as it's in between A and B. So let's use generating functions. So generating function, the walk can either be stationary, 1, or it can take a certain step, t to the x, which that length is counted by t to the x, and then it continues as another walk with slightly adjusted bounds. Okay, so we can describe FAB using a bunch of other FABs.
Will be f a minus x. So
XY is in the step set.
Yeah,
X.
Yeah, the first subscript.
AX
Oh.
minus X.
No, it's not.
Oh, that should be, no, that should be minus y. AI minus y. This is saying, FAB is saying the number of walks that stay between lower bound of B and upper bound of A. Assuming you start at 0, 0. Okay? Did that answer the question? Okay. So we were able to do that. Well, we can actually do it for all of those values, and if we have f negative 1 comma another value, b is less than 0, assumed to be less than or equal to 0, then if we have f negative 1 comma something, that generating function is 0 because we're starting outside of an allowed bound. So we get a finite system that is linear of a minus b equations, a minus b variables. Woohoo! That means we can solve.
Sorry, I'm still thinking
Okay.
about the previous slide. Can you go back on this?
Yes.
Yeah, so I am still a little confused by this. So this is walks that stay between A and B. Is that what you want there? FAB.
Yeah. So yeah, you have some walk. FAB is counting the ones that start here and don't go. This is A. Y equals A, Y equals B. We're starting here, and we have some walk that stays inside. So we're going to take our first step here, and then we have an adjusted height here. If y is positive, then this bound will become smaller, and this bound will become larger. So this is our new relative lower bound is then b minus y, and our new relative upper bound is, if this is step set is xy, then its relative upper bound is a minus y.
so if a minus y is less than 0 or a minus y greater than 0, we find to be 0.
Yeah, so then, yes, f a b equals 0 if a is less than 0 or b is greater than 0. Okay. Thank you. All right. So yeah, that's why we end up with a finite system, a minus b equations, a minus b variables, and we can solve this, and we end up with rational solutions. So we can find explicit solutions. So close football games, if you have all the different ways you can score, how many points relative home team versus away team can be scored. These happen like if you score safety on a touchdown or something. Yeah, not likely to happen, but they're possible, so we're included. So if we're saying they're close games, so we bound that above by 8 and below by -8, basically saying you're never more than one score away from being tied, then the generating function is explicitly given by this. And that's just counting the number of ways the game ends, and you're somewhere, and you're within one score of each other. Okay. And what this is useful for, what if you want to enumerate 1,000 terms? We can use brute force recursion. It actually was still pretty quick, just because it's bounded, everything's cut off, so it's a lot easier, but it's still using just Maple's Taylor function on the rational explicit function we had earlier. We got about 8 times as fast, and a much smaller amount of memory. Bounded bridges, so what if we want bounded walks that come back to the x-axis? Well, in this case, we have to create a new generating function, EABC, that starts at 0C, ends on the x-axis, and never touches the x-axis beforehand. So in this case, the walk that we are interested in either is stationary, or it takes a step directly to the right, x0, and then continues as a new walk, or it takes a step up to some other point. It must come back to the x-axis at some point by our definition of being a bounded bridge, and then it continues as a new walk. Does that make sense? Nope. Okay, now we just have to describe EABC. So if it happens that we can take a step directly to the x-axis, then we take that step and we're done. Otherwise, we take every other possible step and we continue as another irreducible walk. So again, we have a closed system that we can describe, because if C is too large, you end up with a 0 generating function, or too small. So, again, we have a linear, these are not dependent on f at all. So we have a linear system here, so E, A, B, C are all rational. So even though we have a multiplication here, these are all rational, you still end up getting a rational solution. It's not alchemy, it's just, you still end up with that. Yeah. Any questions here? So this is doing the same thing, but football games that end up tied at the end of the game. It's just, interestingly enough, you actually have the same denominator. I don't know if anybody noticed. Okay. And enumerating, about 2.5 times as fast, but still faster. So what if we want semi-bounded walks, so excursions, come back to the origin. Well, we could have the same thing and have this irreducible walk that goes from E0y back to the origin, or back to the x-axis. But every single time we try iterating that, the first step could be even further away, and we would have to create an infinite family.
You said return to the origin.
Sorry, not return to the origin. I meant return to the x-axis.
You're not allowed to return to the origin.
Not allowed to return to the origin, no. Sorry. Thank you. All right. So instead, let GAB denote the generating function for irreducible walks from 0a to nb. And at least one of a or b has to be 0. Otherwise, we could just shift the walk down. Since it is irreducible, it is never going below the lower of the two endpoints. So we can always consider G to have index at least 0. All right, so that's the way to construct them. So we had F00, and then we need to describe G00, and then we have to describe a bunch of Fs, and then we have to describe a bunch of Gs. You end up with a closed system. This will terminate. Let's start with an example. So F00 is this, then we have to describe G00, then we have to describe F01, then G01, then F20, then G20, and then F11, and what haven't we described here yet? G10 we haven't described, so we have to describe G10. And then we finally have to describe this one from earlier, but after all of this, now we're actually good. Every generating function we've possibly used, we have an equation for it. So this is a closed system describing it. Yay. But it's no longer linear, so we can't just solve for it, but we can use Grosvenor basis to come up with a minimal polynomial. So for the previous step set, minimal polynomial basically gives us this. The generating function satisfies this relation. And that relation can be used, here's another example, the relation just by iterating solution, like plug in f equals 1, you'll get something else, and plug that in, you'll get at each step you'll get the next coefficient. plug that in, and we can try enumerating that way. So vector setup, that means creating all the systems, doesn't take much time. However, if you iterate a vector of solutions for all of the generated functions, that took about 4 minutes. If you're trying to find the polynomial, that was really fast, milliseconds. But iterating just the single polynomial, it took about a minute. So in all of these cases, for some reason you can use Taylor and just say root of on that polynomial, for example. This polynomial, and that works. And that's pretty fast, but still not that fast. As brute force, it happens to be better in this case. Very little time left. So I can also describe meanders, which are semi-bounded walks that end anywhere. Do the same, basically the same thing. Enumeration is roughly equivalent. My method is better than guessing at getting the minimal polynomial. So there is at least that. And once you combine that with a method of converting the minimal polynomial, well, any algebraic equation, to a recurrence, this is a recurrence satisfied by those coefficients. This will enumerate it faster. So we can beat brute force. We just have to work a little bit harder to get there. So yeah, to get 1,000 terms, we can do that after finding the polynomial, converting it to a recurrence, and then using that recurrence. Just over half of a second, but brute force took 1.5 seconds and only got half the number of terms. Again, we know there's a linear recurrence. Why can't we just guess at the linear recurrence? Well, there are cases where guessing is better. There are also cases where converting is faster. The key is deciding which one's faster is the degree of the minimal polynomial, the number of steps you have, and the size of the largest step that you're considering. A free unbounded walk, not interesting. I'm just going to skip that. Altitude doesn't matter. So what if we want bridges, unbounded bridges? So G is the generating function for unbounded bridges. Let's say H0 is an irreducible walk that goes from 0 to 0, from the x-axis to the x-axis, and never touches the x-axis anywhere in before. We now have a new, so we return to the x-axis somehow, either by some walk that returns or a step directly to the right, and then we continue as before. A lot of these all start as that form. We then have to describe H0, which either consists of an irreducible walk above the x-axis, or a walk below the x-axis, which you can just flip it and it's the same thing. Or we have some irreducible walk, for example here, from 0 to some step, and then we jump over the x-axis, which is counted by this middle step here. And then we have another irreducible walk, hi plus y, back to the x-axis. And then this is just counting if you went down, jumped across, and then back to the x-axis. Describing the other h's in a similar way. And these build on the semi-bounded cases. Okay. I'll ignore those interesting asymptotics.
The dissertation be available?
Yes, the dissertation available online if anyone is interested. Computers were instrumental in all of my research. I wouldn't have been able to do much without them, so thanks to computers. It was all about revising the results of mathematicians before me to work in a more general way. Thanks to my wife, Caitlin, for supporting me. Thank you to the committee for serving as such. Thanks to Dr. Z for providing these research projects. Any questions?
Public part of the defense, so please step out. If you're welcome to come, the committee has to say, if you like to for dinner, please